So let's get back into chapter 22. Okay, so remember here we were dealing with the chemistry of the alpha carbon and alpha hydrogens on a molecule. Okay. And remember again, the alpha carbon is the one next to the carbonyl, and alpha hydrogen is on it. Last time we looked at the reaction with LDA, remember that strong base took the alpha hydrogen and made the enolate ion. Okay. So let's do a real molecule here once again. So there, LDA would take one of those alpha hydrogens. And then remember that was resonance stabilized. To give us the full enolate ion, which remember was a combination of both resonance structures. Okay. Well, today what we want to do is do some reactions with the enolate ion. How does that thing react? Okay. Well, the way it's going to react is, if you look, you have negative here and negative on the oxygen. This thing is going to react as a nucleophile. Okay? It's going to react as a nucleophile. But if you look at the enolate ion, you have two places that it could act as a nucleophile. It could act here, carbon with this lone pair, or here, oxygen with its lone pair. So we have to make a choice. Which one do you think is going to act as a nucleophile the best? Okay. Any ideas from what we discussed last time? What do we say about the carbonyl? Very stable. Okay. So it's going to go with the more stable one. So this one here is going to act as our major nucleophile. So what do nucleophiles like to react with? With substrates. Okay? And remember that a substrate has a leaving group. So since this one here will be the nucleophile, we can do a nice SN2 reaction. And add that methyl group on, so we extend the chain there. Okay? So this here is an alkylation reaction. Okay? This is the main, one of the main reactions that we're going to do with the enolate. We'll see some others down the road. Okay? All right. So let me give you a problem or two and See if you can draw the result. Okay, give you a minute to work that out. Okay, if you have a problem working it out, work with a neighbor. I'm gonna pick somebody up to come and put the answer up here.
I have a question. Since we know which one we can use as, do we have to?
All I'm looking for here is the final product. You don't have to draw the full mechanism. You can if you want. Okay, let's bring yellow up here. We want yellow.
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 I'm working it out.
Come on up here.
I'm yellow.
We'll work it out together. Watch it, George. You might be next. Here. Yeah, this is the alpha carbon.
Dr. Miller, when you were looking at the resident structures after you react with LDA, how did you pick which one was a nucleophile again?
They go with the carbon because that had the carbonyl. The carbonyl is stable, so that makes it a better nucleophile. Okay, well, you got the right product, okay? This mechanism needs a little help. But all I was looking for was the product, so that alpha carbon gets it, so this carbon was attacking here.
That was the train of thought, like where was going.
Okay, it's the thought that counts. Okay, so any questions on alkylating the alpha carbon? Okay, pretty straightforward. Okay, so all I have to do is remember it's this carbon here that attacks the substrate. Okay. All right, well, let's do something somewhat similar and somewhat different. Okay. Here what we want to look at is the chemistry of amines. Remember the enamines, what those were? Back in the amine chapter? What were they? Okay. That's where we had a double bond and an amine group. Remember that? Okay. So we have an amine, an amino group attached to a carbon-carbon double bond. So let's see how we can work with the chemistry of this. All right. Well, here you have a lone pair next to a double bond, so we can draw a resonance structure. Okay. So I can move the lone pair there, and then the pi electrons will dump on that carbon. Okay, so we get something like this. Okay, and here we get a similar situation to what we just looked at with the enolate ion. Okay, remember the enolate ion had two different lone pairs that could be a nucleophile. Well, this one does too, the nitrogen and this. Which do you think will act as the nucleophile? Nitrogen or the carbon? The carbon. Okay? There's this double bond here, just like the carbonyl, very stable. Okay? So this thing here is going to act as a nucleophile. So suppose we brought in a substrate, again, like methyl bromide. Okay? That could attack to add on that methyl group. So you can see we're kind of doing the same thing, okay? Alkylating, in a sense, the adjacent carbon, in a sense, the alpha carbon, okay? But now here's something new, okay? What we can do is take this and react with the hydronium ion, H3O+. And what that does, we won't go through the mechanism of it, but it converts that imine, that iminium carbocation to a carbonyl. Okay, this is sometimes called the iminium ion. Okay, remember the imine, the imine was a C double bond N. Well, here when you have it with a positive charge, we call it the iminium ion. Okay, so this is the chemistry of enamines that we want to take a look at. Okay, so this is the model that we're going to follow. Okay, let's do some problems to see how this works. Okay. So let's look at something like this here. Okay, see if you can draw the final product for that, okay? So don't let this scare you. Treat this top portion like it was at NH2, okay? So you have the ene amine, okay? So don't let that scare you. See if you can draw the final product for that. It's got Walmart coming.
Please don't laugh, I'm totally.
We won't laugh at it.
Okay.
You'll be on camera.
Just draw the final product. You don't have to go through all of it.
Oh, so I ain't gonna do
You say you would?
What do you guys think of that? Okay, so we said one laugh at her.
As long as I think.
Okay, a good try. Want to come up?
I just think it's missing one thing.
Come on up, show us.
Oh, geez.
Oh, I forgot my group.
Yeah.
That's fine. Okay, that's getting closer.
I have a question.
What's, all right, question.
Since you treating the top portion like NH2, would you take the whole thing off and just leave the carbon?
Yeah, so why don't you come up and help me? Come on up and help me.
I took the.
Get there stepwise. You only need an eraser now, don't you? There you go.
That's kind of
Clean that right.
But I emailed.
Okay, there's three of us, but we did it. Okay? So whatever this amine is, all right, that gets knocked off with the H3O plus, and this is considered like an alpha carbon. Okay? So you see how this is related to the alkylation we just did.
So in what step would it get knocked out? At the very beginning or?
The last step.
Okay.
Okay? But for this, I'm not going to ask you to do the mechanism. I just want you to be able to draw the final product. Okay? So we'll just keep that simple. All right? So remember, chapter 22 exam is next Wednesday. All right? And I'll cue you in on Friday or Monday as to what mechanisms you need to have down. Okay? Let's do another one here. Okay, exact same reaction, but you got a different substrate, an acid chloride. Okay, you remember how acid chlorides react? So go ahead and complete the reaction. Again, if you're in trouble, go to a neighbor and ask for help.
Okay, I know all these folks go away. And I know these got a minus on it. It's gonna erase these. Still, it's gonna take the front wheel, right? And figure it out. Yeah, it's gonna take it out. And figure it out. And this gonna take it. I know we was wrong. Well, our neighbors don't give us you know what the movie done like.
Why don't you come up and give us your answer? Very good. Okay, so acid chloride, so this carbon here, acts there, kicks off the chlorine. Okay, then the H3O plus cleans that up, converts it to the carbonate. Okay, so this reaction here was an acylation reaction. This is sometimes called the Stork-amine reaction. Okay, a guy named Stork founded it, so. All right, so you got two different reactions with the amines. You got one, the alkylation, and then two, you got the acylation. It's called the Stork reaction. Okay. Okay, so let's go ahead and move on to our last reaction for today. Okay. Okay, these reactions, we're going to call them alpha halogenation reactions. Okay? So what do you think this reaction's going to deal with? Halogens? What about halogens?
Next to a carbon monoxide.
Yeah, some on the alpha carbon. Okay? How do we put a halogen on an alpha carbon? Okay? So we get two ways to do this. One is with a base catalyst. Okay? So here's the setup. If we have a molecule with an alpha hydrogen, our base now is not going to be LDA. Okay, we're now going to start shifting to OH minus. And then remember, X stands for halogen. Okay, so we'll have a halogen substitute for the alpha hydrogen. Okay, so these will typically be bromine or chlorine in doing these reactions. Okay, so let's go ahead and look at a few of them here. Okay, so let's go through this stepwise. So the OH creates the enolate ion. Okay. So again, you could draw the resonance, but this is the one that acts as the nucleophile. And let's bring in, say, chlorine dihalogen. Okay, so it attacks one of those chlorines and the other acts as a leaving group. And so we get an alpha halogenated molecule. Okay. Well, does this thing have another alpha hydrogen on it? Right there. Well, and if I still got base in there, guess what it could do? It could do it again. Okay. In fact, this thing's going to be even more acidic than this one because I got two electron withdrawers here, the carbonyl and the chlorine. So now, if I react that with base, I can take that one off, So that lone pair is getting stabilized through the carbonyl and my electron withdrawing chlorine. Okay? So this conjugate base here, write it down, is more stable than this conjugate base. Okay? This conjugate base is more stable than that one because of that chlorine. So now I can react again. And now get a dihalogenated alpha carbon. Okay. All right. Any questions on that? We'll do another example in a second. But let's compare that with an acid catalyzed reaction. Okay. So instead of using a base, what happens if we use an acid? Okay, so just using a carboxylic acid like acetic acid. Okay, what's the difference here? Write it down. The difference is, this is how we only get one halogen added on. Okay, so it stops after adding one. Okay, this is how to get a monohalogenated alpha carbon. Okay, the base keeps going, not the acid. It just gives you one. All right, so that gives us that as our final product. Okay, you can look at the mechanism. It's very, very involved. I won't hold you accountable for it. But you can look at it in your textbook. Okay, it uses the enol tautomer to do it. Okay, and all I want you to do is be able to tell the difference. Okay, so let me give you a couple to work on here.
Don't erase it.
Don't do that. Okay, so if you can work on that one. Work on that one.
I'm taking up the extra one. Have that to be on. Actually, I ain't even gonna make any pictures.
Okay. Says top reactions, what a base catalyzed. So it's gonna be super aggressive. Okay. So if I look on the right-hand side, how many alpha hydrogens do I have? So how many bromines will add on? 3. Take all 3 of them. Don't stop at 2. Takes them all.
I did it like this. I ain't right no make this.
Okay, so make a note of that. In the first example we did, we only had 2 alpha hydrogens. Okay? Well, here we have 3, so take all 3 of them. Okay, so don't stop. The bottom one, this is an acid catalyzed. So what's going to be difference here?
We're gonna stop at the first.
Just going to stop at the first. How many of you got the top one? Anybody? A couple of them. Question?
Yeah, so when we have an acid catalyst, we only get the mono,
Right.
halogenated, but because we have 2, we don't get 2 mono halogenated carbon.
Right, yeah, you just stop with one.
So you just choose one of them.
Any other questions?
With that first one, do we just repeat the OH stage until we,
Right,
okay,
yeah, keep going.
So it's
Almost-
BR,
almost like that
OH, BR.
exhaustive alkylation kind of
okay.
thing.
There's nothing fancy with those extra
No.
H's.
Question?
So the first one, we have to make it for the exam, right?
This one here?
Yeah.
Yeah. But not this one. You follow that, George? Okay. All right, so next class, we'll continue the chemistry with the OH minus on this and look at some new things, okay? We'll see you then.
I gotta work.